Now we're going to begin Lecture 2 for Module 9. So in this section of Module 9, what we're going to look at is filtering properties of dynamic systems. So this is going to be from section 9.4 in our textbook. We're also going to look at response to general periodic inputs from section 9.5 and system identification from frequency response from next section 9.6. Let's take a look at some filtering properties for our dynamic systems. So there's three types of filters that we're going to look at here. We're going to look at a low pass filter, which responds more to our sinusoidal inputs, having low frequencies. And we're also going to look at a high pass filter, which responds to the higher frequency inputs. And the third type of filter we're going to look at is a band pass filter. And this type of filter responds to inputs having frequencies in the mid-range. So typically we use the word and term filter when we're talking about electrical circuits, but we may think of other systems as types of filters as well. Now, for example, a spring mass damper system having a large damping ratio will act like a low pass filter. So this will respond more to our low frequencies. Now, where do we see these types of systems? Well, these are going to be represented in vehicle suspension. And this is where the passenger compartment is going to undergo this negligible motion when the vehicle moves with high speeds over closely spaced road surface variation. So you're going over a bumpy surface. So all of these types of systems here where we want to minimize the amount of motion or a negligible motion when it's going over these bumpy surfaces. So going back and talking about these electrical circuits, oftentimes it's easier for us to visualize what's going on within the system if we reference it back and draw out an electrical circuit for that system. So some simple electrical circuits are composed of resistors, capacitors, and op-amps. And these can be designed to act as our different types of filter systems, our low pass filter, high pass, and band pass filters. And these can be found in many different applications. So down below, we can see we have two different RC circuits. The top one here is configured as a low pass filter, whereas the bottom one is configured as a high pass filter. And if we look closely, we can see the difference, and it's just a very subtle difference, and it's the placement of our resistor and our capacitor here. So for our low pass filter, we have our resistor up top here, so we have our voltage source coming in over here, coming up through, and then there is our resistor up top and our capacitor down here, and we can see our output voltage over here. Whereas for our high pass filter in their bottom diagram here, there's our voltage source over here. Coming in, now we can see now we have our capacitor up here and our resistor down here. Same voltage output over here though. The next term we're going to talk about in this section is our bandwidth. So for forcing frequencies, we really want to have a specific measure of range to which a system is especially responsive. So this single measure can be used as a design specification for these different systems. The most common such measure is known as our bandwidth. Now, bandwidth is commonly defined as a range of frequency over which the power transmitted or dissipated by the system is no less than 1/2 of the peak power. Now, for many of these systems, the power transmitted or dissipated is going to be proportional to our m squared, where m is the magnitude of the frequency transfer function. Continuing on with bandwidth, take a look at an example here. So we have the power dissipated by a resistor. This is going to be proportional to the square of the current. And the power dissipated by the damper is going to be proportional to the square of the amplitude of the velocity difference across the damper's endpoints. So we defined, again, our bandwidth is commonly defined as a range of frequencies. So this is omega 1 and omega 2 here, over which we have this relationship here now. There's our m squared of omega 1 is less than or equal to our m peak squared over 2 greater than or equal to our m squared of omega 2. Equivalently, we can rewrite this same relationship here, and we can say m omega 1 less than or equal to m peak over the square root of 2 is greater than or equal to m omega 2. So you can see that lies in between m omega 1 and m omega 2. And for this reason, the lower and upper bandwidth points are called the half power points. So we're going to take a look here at some possible frequency response plots. So if we take a look at A first, we can see in part A of this plot here, our peak, MR, is going to be large enough so that the value of MR over the square root of 2 is going to be greater than that of M of 0 here at 1. So we can plug those values in, or look at it within MATLAB, Excel, any other type of numerical analysis system, and double check that, okay, yes, my MR over the square root of 2 is greater than my M of 0 here. Therefore, the lower bandwidth frequency 1 exists and is greater than 0. So such a system here is going to be known as a bandpass system. Now, if we're looking at part B of this plot here, what we can see here is we have this value here that M of 0 right there is going to be greater than our MR value, which is right here, divided by the square root of 2. So that our omega 1 is equal to 0, and this is going to be the plot for a typical low-pass system. Now, down in plot C here, what we have is a high-pass system. What we can see here in the high-pass system, at the upper bandwidth frequency here, keeps going up and is infinite. And this is going to respond to more high-frequency inputs. Last, we have part D of the plot here, and this shows a magnitude ratio plot with 2 peaks. Now, this can only occur with a model of a 4th order or higher. We're going to look at an alternative definition for bandwidth here. So we have the fact that amplitudes of low-frequency forcing functions are larger than the amplitudes of the high-frequency inputs. So therefore, our low-frequency inputs might account for more power. So what this means is that these frequencies that are beneath our lower bandwidth frequency, our omega 1, these may contribute pretty significantly to the response, and they can't always be neglected. And because of this, a new modified definition of bandwidth is going to be used sometimes. With this alternative definition, the lower bandwidth, our omega 1, or lower bandwidth frequency omega 1, is assumed to be 0. And our upper bandwidth, our omega 2, is defined to be the frequency at which the power is 1/2 of the power at the 0 frequency. So these frequency response curves are not necessarily always used as a measure of system performance. In this case here, we're using earphone frequency response and human hearing on the curve. So for example, we have some designed headphones so that the ratio, our magnitude ratio, is 1, or our M is equal to 0 dB. This is over the entire range of frequencies that are detectable by the human ear. 20 hertz to 20,000 hertz is the typical normal range that we can hear with the human ear. So consequently, a measure of headphone performance is the amount of deviation away from its M curve, so from 0 dB over this frequency range. So we can see the curve down here. We have our frequency in hertz on our x-axis, and we have the magnitude ratio in decibels here on our y-axis. And then for some particular headphone, we can see we have one curve drawn out here. It's a little bit difficult to see. I'll trace over top of it. And you can see as our frequency varies, how our magnitude ratio in decibels varies as well with the frequency. Now this would be a great way to compare different manufacturers, different brands, and different models of earphones and see how they perform head to head. We could experimentally acquire the data for over a range of frequencies, our human hearing range of frequencies. We could test and get results for our magnitude. Then we can plot that magnitude on this curve down here and label each curve for each type of headphone and see how they compare head to head. Now, one thing that we can see from this graph here is that the earphones amplifies the signal in this 20 to 400 hertz, and again in the 5,000 to 8,000 hertz ranges. Now, contrary to that, we can also see that if we get above 9,000 hertz on our graph over here, it's pretty much going to attenuate most signals. So a graph like this can also be used not only to compare different models of headphones, but optimizing a certain headphone. So if you had maybe a noise canceling headphone that you wanted to take a look at, and you knew that, hey, I want to cancel out noises or attenuate signals in certain frequencies, you could use this graph here from experimental data to look at that and make sure it's attenuated in certain areas. If you wanted to only be able to focus in on certain and amplify certain frequencies more than others, again, you could use this graph here to compare those. Next, we'll take a look at a response to general periodic input. So we're not going to limit these cases to a single sinusoidal input. In some cases, we might have a sum of functions that constitutes the input. So the total force response can be found from the sum of the force responses of each term. So there's a basic theorem for analysis with some assumptions that's going to state that any periodic function can be expressed by a constant term plus an indefinite series of sines and cosines with increasing frequencies. This is going to be known as our Fourier theorem. This is going to be associated with our Fourier series, and it's going to have the general form that we can see down here. So we can see we have f of t is equal to a naught over 2 plus a1 times the cosine of our pi t over p plus a2 times the cosine of 2 pi t over p plus so on and so forth for the rest of the equation here. And we also have this for a b1 and a b2 all the way on up as well. So let's discuss another application when we can use this frequency response plot from experimental data. So if we're talking about system identification from frequency response, now in cases where a transfer function or differential equation model is difficult to derive from general principles, or where the model's coefficient values are unknown, in this case here, an experimentally obtained frequency response plot can be used to determine the form for an appropriate model and the values of that model's coefficients. So this is another example of when we can use experimental data from a frequency response plot. Now, as we're talking about experimental data, the next thing that comes up is kind of some actual physical testing, lab testing, and some of the procedures, some of these test procedures. Now, depending on what circuit we're dealing with or what system we're working on, it's often the case that a sinusoidal input is going to be a lot easier to apply to a system than a step input. Now, many devices, AC circuits, rotating machines, naturally produce a sinusoidal signal or motion. So this is the reason why using a sinusoidal input with these systems is going to be a lot easier than trying to bring in a step input. So if we have one of these apparatuses and it can be devised to provide a sinusoidal input of adjustable frequency, then in that case, the system's output amplitude and its phase shift, which are two things that are important we're going to want to find, relative to the input, can be measured for various input frequencies. So we can change what our input frequencies are, collect the data and see, okay, based on this frequency input, I'm seeing this type of output and this type of phase shift. So this is where we'll go back to our logarithmic plots here, and we can plot the data for a sufficient frequency range. The form of the model can then be determined from that logarithmic plot. Now, one thing to mention here when we're talking about physically testing this is going to be easiest for systems that have electrical inputs and outputs. So we have a place to hook up a sinusoidal input. We have a place to hook up a DATAC, some data acquisition system on the outputs for these systems. Now, as we're continuing to work with and utilize these frequency response plots and the data for identification purposes, it's going to become very important for us to understand how we can use this in order to reconstruct a transfer function form from the asymptotes and our corner frequencies. So if we're talking about our asymptotes here, we can take the slopes of these asymptotes and use those in order to calculate and determine the orders of our numerator and denominator. Now, from our corner frequencies, these can then be used to estimate our time constants and our natural frequencies. Now, all real data is going to have some scatter involved. So therefore, a perfect model fit is not going to be practical for this, because there is going to be some scatter involved no matter what. However, for illustration purposes, in order to clearly show these methods, we can use examples that have very, very little scatter, and therefore the derived models are going to be unambiguous.